So balancing redox reactions is completely different from normally balancing reactions, because in that we just look at the elements on the left and right and we try to make them the same by adding coefficients. So we don't have to relate balancing redox reactions to normal balancing at all. One of the things that you're going to have to keep in your mind is about their charges. Remember that oxygen, unless it's with hydrogen peroxide, is always going to have a charge of -2. This makes things easier for us in terms of predicting the charges for the element, or specifically transitional metals that it's bonding with. Because for any transitional metal or even other elements, it's not 100% necessary that as ions they would be sharing a fixed number of electrons. It could be more, it could be less, and for this very reason we often use the elements that we are sure about, like oxygen and even hydrogen, group 1, group 2, and halogens that have -1. Okay, so when we're trying to balance this, I'm going to leave both of these, two of these slides for you to look into why I'm calling one of them oxidized and why I'm calling the other the reduced one. Remember the mnemonic oil break. Okay, so we're going to learn about two different ways of balancing redox reactions. So the first one is the standard balancing redox reaction, in which it's not mentioned in the question whether it's being done in an acidic solution or in a basic solution. I have written down the differences between both of them. I understand that there's a lot of steps to it, but if you think you are weak on this area, please try to practice them again. I'm going to share the answer key to 4.9 in the shared folder, because I do remember that we checked our redox reactions the standard way, not the acidic or basic way. Okay, so your first steps are to identify which one is oxidizing and which one is reducing. Okay, and then what you do is that once you've separated them, you've written them separately. You've written them separately, just a second, like, yes. When you've written them separately like this and like this, your next step is to balance the atoms. So now we're going to now that we've written our oxidation and reduction reactions separately, remember that whether you're doing it the standard way, acidic way, or basic way, you have to treat both of these half reactions as separate equations. Okay, so let's look at the oxidation one. So you had nickel with a charge of a 0 before, and now it has a charge of a +2. And then in the reduction side, we have our electrons. Cobalt gained an electron. That's why we've written it before the arrow. And here we've written the 2 electrons after the arrow because it lost it. So once you have checked your atoms, okay. Now here, please have a look how nickel was 1 before and it's 1 after. I'm not talking about the charge. You have to be very clear about the word charge and coefficients and knowing the overall charge, and also knowing that a charge doesn't mean that you have 2 of those. So nickel was 1 before, 1 after, so we don't have to balance the atoms. You have 1 nickel atom before, 1 nickel atom after. If you look over here, you had 1 cobalt atom and you have 1 cobalt atom after. If you didn't, it would be a different case. You would be balancing, you would be adding coefficients like you do in normal balancing, and we're going to do that in one of the other examples when we're balancing acidic solutions. Once you have written the oxidation and reduction half reaction separately, you just check the number of atoms. Next step, you check the number of electrons. So notice over here how my charge was a 0, but on the other side of my of the very same oxidation reaction, I have a charge of a +2. So this means that my left and right charges, let me make a line over here, my left and right charges are not equal to each other, which defies the law of conservation of mass, because we say that, I mean, in nature, whatever is lost is gained, or whatever is gained is lost. I'm sorry, whatever is lost is gained. It can't just disappear into thin air. Now, in order to make this side a 0, I have no other option than to add 2 electrons. I'm sorry, let me just, yeah. All I did here was add 2 electrons, and this way now my overall charge is also a 0. You could do this manually also, but what I mean by this is that if nickel was a 0 before and now a nickel is 2+, it means it lost 2 electrons. Now, because this is a very simple oxidation half reaction, and it's just 2 electrons being lost and just one element that we're talking about, it's very simple by just, you just adding that, oh, okay, I'm just going to write 2 electrons. That means that the nickel lost 2 electrons. But it's not going to be this simple when you're doing it for other reactions. You're actually going to have to jot down the charges on the left and right, like I just did right now. What you have to make sure is that whatever you have on the left, the charges, total charges, is whatever you have on the right. And you can do that by writing in your equation that electrons were lost, because remember that in chemical equations, we never write minus, okay? Okay, let me erase that. Now let's look on the right side. On my right side, I can see that cobalt, both of them, my atoms are balanced. Now let's look if my charges are balanced. Now I don't have any space below, so I'm going to do it on top. Here, the charge was a +2. And on my left, I have a charge of cobalt is +3. Now I know that these are not equal, so how can I make them equal? Remember that I cannot write here a -2 electron, -1 electron. I can't do that because there are no minuses in a chemical equation. So I am bound to write it on this side, and writing this, mentioning 1 electron over here, means that I have 1 negative now, which is equal to a +2. So now I know that my left and right sides are the same charges. Once I have balanced the charges and my atoms first and then my charges, remember that when we're balancing atoms, we balance oxygen and hydrogen at the very end, okay? Hydrogen at the very, very end. Okay, now that my equations their own charges are balanced, I'm now going to compare them with each other. I have written both of them together like this. Now, the problem with both of these equations is that at the bottom, in the oxidation one, I have 2 electrons, which are not canceling out with the number of electrons I have in my reduction reaction. I have only 1 electron. So I'm going to multiply my entire equation with a number that would help me cancel out the electrons. Again, we're doing this in order to abide by the law of conservation of mass. I multiplied this entire equation by a 2 in order to make my 2 electrons cancel each other out. They're canceled, and this is what I'm left with. So how is it different from when I'm balancing my equation in acidic conditions? So I do the same steps. I identify and write my oxidation half reaction and the reduction half reaction. Then I treat them differently, like I work on them separately. I check if my atoms in my oxidation reaction, both sides, are my atoms the same? If they're not, I add coefficients, and I do the same for reduction. And then I check if my charges are the same on the left and right side of my half reaction. So let's suppose if I was working on my oxidation reaction, this is the step that I did. I had added 2 electrons to it because my nickel on the left was not equal to the one on the right. Okay, so these are the steps that I generally have to do. Also, please remember, oxygen and hydrogen are done at the very end. Okay, so let me switch to a paper that I'm going to be solving this on. I'll be using an example from the I do, we do, you do, so that later on when you try it on your own, you are able to check the answers side by side. Okay, so let's start with writing their charges alone, okay? So again, because it's the simplest for me to start with oxygen, I will just write oxygen's charge because we can see that it's not a hydrogen peroxide, so it's a -2, okay? Now overall, I can see that this Cr2O7 has a charge, an overall charge is a -2, so that means that the total, when I add chromium and oxidant's charges together, should end up in a -2. Now, I have figured out oxidant's charge, which is a -2, and I know that there are 7 oxidants in there, so that just means that there is a total of -14. -14. So what minus -14 would give me a -2? That would be a +12. I know that there are 2 chromiums, so that means that's half of +12. So that means the charge of each chromium is a +6. Now let's move to the other compound. Overall, I can see that this is neutral, so whatever is in there should be equal to a 0. Okay, again, I'm going to begin with my oxygen. I know that its charge is a -2. For hydrogens, I know that it's a +1 and a +1 again over here. Okay, and for carbon, because I have 6 hydrogens, so that means I have this means I have +5 here and +1, so I have a total of 6 hydrogens here. I have a single hydrogen, so that's only a -2. So what minus +6 and -2 would give me a 0? Gives me a -4. And when I add them all together, I get a 0. And that is going with the overall charge of this compound. Now let's go to chromium. That's very simple. It has a charge of a +3. With carbon dioxide, I know that oxygen has a charge of a -2. This is an overall neutral carbon dioxide. So I'm looking for a 0. So that means because these are 2 oxidants, it must be a -4. Let me just write that above over there. Okay. So this must be a 4, and I have 1 carbon, so that means these are the charges. So please make sure that you are able to first assign them their charges, and then you add or subtract them and count how many you have in order to figure out the overall charge. Okay, so what I can see over here is that my chromium was a +6, and now this is a +3. So in order for that to happen, it has gained electrons, and we know from oil rig that reduction is gaining. So I'm gonna use this over here. For my oxidation, I can see that my oxygen was a -2. It's still a -2, so nothing happened to that. My carbon was a -2 here, but this side, it has become a +4. So this can only happen when it let go of its electrons. It went from a -2 to a -1 to a 0, and then it kept losing the electrons. This is why we call, because it's going down like that, and in order for this, you must be letting go of electrons. Okay. So I know that this got oxidized. Now I'm going to write all of these in their designated places. Okay. So what I can see for my reduction. Okay, I'm going to start with reduction just because there's a few things I want you to add up over there. You could obviously do the oxidation first, but it's just easier if you start with the reduction. Okay. So I have, I'm going to just write my reduction half reaction, which is Cr2O7. It should have an overall charge of a -2. It's okay if you write the minus sign before or after the number. That's not important. And that is 3 plus. Okay. Now, my first step, as usual, would be to check if I have the correct atoms. I'm going to balance my atoms. And I know that I have 2 chromiums here and 1 chromium here. I'm talking about the atoms, not the charges. I know that they are different. That's why we're calling it reduction. So I need to make 2 of my chromiums. Okay, remember to always leave oxygen and hydrogen at the end. I now have the correct number of chromium. But what I can see is that in this half reaction, I have an oxygen and it doesn't exist this side. So I need to add water to the side where I want to balance oxygen with. Now, I'm just going to add water this side. This is what balancing a redox reaction in acidic solution means. So I now have water, which means I'm going to compare my oxidants again. So I have 7 oxidants this side, I have 7 oxidants this side, and I have 1 this side. So what can I do in order to have the number equal? I'm just going to add a 7 over here, a coefficient of 7. Now I have 7 oxidants, but this also made me have 7 hydrogens. And for that very reason, I'm now going to add hydrogens on my left side. Oops, sorry. Okay. So I'm now going to add hydrogens on my left. I know that I have 14 hydrogens. So I'm going to write 14 hydrogens here. Now remember, because hydrogen is alone here, it has to exist as an ion. Hydrogen is a diatomic molecule. When it's alone, it usually exists in pairs, but that's not what we're trying to do here. We are specifically only adding water on one side and hydrogen on the other side in order to balance our equation. This is what being in an acidic solution means. If you can recall what acids are, that acids consist of hydrogen ions. They donate protons, as in hydrogens. So this means that this is acidic. This is what this is implying. Okay. Now that we're done doing step one, in which we balanced our atoms, step two, in order to balance our atoms, we had to add water on one side and hydrogen on the other in order to balance those. Now we're going to compare the number of electrons we have on our left and on our right. Because we have to abide by the law of conservation of mass, which tells us that whatever electrons were lost or gained on the left and right should be equal. For this, I'm going to do my usual method of comparison. So on the left, let's look at what we have in total in terms of charges. So I have plus 14 charges and a minus 2, right? I just wrote what I have here and I wrote what I have here. If there was a neutral compound, I would have written a 0. So in total, I have 12. Okay. And I have plus 12 electrons, right? I have a charge of plus 12. Now, when I look at this, I'm sorry, now I'm going to look on my right. Okay. So this has a charge of a 3 plus, right? Plus 3. And there are no charges with water, so it's just going to remain as plus 3. Now, these are not equal. I have a plus 12 on the left and a plus 3 on the right. What can I add on the left to mathematically represent that? I'm sorry, we have 2 chromium, so this is going to be a total of plus 6. Okay. So what can I add over here that would make my numbers the same? Remember that I cannot write a negative in an equation. So I have to write it on the left side of my equation. So what can I write here in order to show that electrons were added to have the same numbers? If I write 6 electrons in my equation, this would mean that I now have negative 6 and my total would be plus 6. Again, now I have the same numbers on the left and on the right. You can compare this with your I do, we do, you do also. There are other examples that have been done the same way. Also, if you're wondering why we added water here and not here, it's because when you're trying to balance your oxygen, basically you're trying to make the left and the right the equal. So wherever you have the oxygen, you don't want to increase your oxidants by adding water the same side. You want to balance it in comparison to the other side. That's why we wrote the water on the right. Okay, so this would be done. And let's look at our oxidation. Okay, for oxidation, I'm just going to write my half reaction, which is C2. I'm sorry, which is C2H5. OH, and that's turning into carbon dioxide. Okay, now I'm now going to balance my atoms, which is my first step every time, whether it's acidic solution, basic solution, or standard solution. I want my carbons to be the same, so I wrote a 2 over here. You can now notice that my oxygen is 2 on the right and 1 on the left. I want to increase the number of oxidants on the left, and I can't just change the formula of the compound or add oxygen alone. So for this very reason, I'm going to add my H2O. Oh. So when I was trying to fix it for carbon and I added the coefficient of 2, I was able to balance my carbons out, but this has now given me oxidants 4 on the right and only 2 on the left. So what can I do in order to have the same number of oxidants? I want 4. So if I write a 2 on the left, then I get 2 plus 1. I'm still not getting enough. So I would have to write a 3 over here. So I now have 3 and 4 oxidants on the left and 4 oxidants on the right. However, notice that I have ended up increasing my number of hydrogens. So I'm now going to add hydrogen on the right side, hydrogen ions on the right side, to balance my hydrogens out. I have a total of 12 hydrogens on the left, okay? So I'm simply going to just add a 12 over here. Now let's see, I have 12 hydrogens. I have balanced all of my atoms. I'm now going to compare my charges on the left and right. I'm going to compare them from one another. So my water over here is a 0. So both of my compounds are zeros. So that means overall on the left is a 0. Now let's check the right side. For carbon dioxide, it's a 0. But for hydrogens, I have a plus 12. Okay. Now I'm simply going to add my electrons on the right side, whose charges are negative 12, and now I have a 0 again. Okay. I'm simply going to check if my coefficients, now I'm going to go back to comparing my oxidation and reduction. Let me go back to the I do, we do, you do, so that now when I was doing my final step of adding my reduction and oxidation reaction together, I noticed that the electrons top and above were not canceling out. And for this reason, I multiplied them with the entire equation with a 2. And then I simply canceled the electrons out, and whatever was canceling out, I did that. And I am left with this 16 of these, and the rest of the answer goes with it. Okay.